Alright, in this video I'm going to show you how in Excel we can look at the idea of temporal partitioning. Remember, that just means time series partitioning, how we might determine how to pick our validation and our training part of our time series. And then we'll also look at how we collect and create the different predictive accuracy measures like the MAE and the MFE. And along the way I'll show you how to do naive forecasts. So this is a data set. Actually, several of you used it on your case assignment. So in monthly milk production, this is from datamarket.com. This is a nice little place to get some time series data as well as lots of other kind of data as well. So this is actually a subset of this data market area specific for time series data. And what it's showing us is milk production, pounds per cow from 1962 through 1975, and it's monthly data. And if we initially just create a plot of this data, we can see it is pretty seasonal, and we have a slight upward trend that actually kind of starts to level off here as we get past around 1971. So the first thing I needed to do was figure out how we would actually divide this up into our training and our validation data set. And typically the training is a little bit bigger, and so the default that people start around is about 60% for training and 40% for your validation or testing. So what I did is I just took 60 and 40% of the total data points, which was 168 months, and I came up with 100.8 and 67.2. Obviously we wouldn't have that many time periods, so then I just kind of looked at the data and found some natural breaking points. And this is, monthly, and it's showing us by years. I decided to keep this as full years, and this is full years. So it turns out at 108 data points, that will get me through 62 to 70, and then the last 60 would be 71 to 75. So that's how I decided to divide this up, and I just put a line here to kind of show me where those are dividing. So in Excel you can't do reference lines like we could in Jump, but you can just drag a line on top of the chart if you would like. So then I have my data over here, and I created 3 different forecast values. So remember, our Y is our actual. Our forecast we designate with an F, and I did a naive seasonal, and then a 3-period moving average. That's a really simple forecasting technique. You may or may not have seen it, but it's extremely easy to do. When I looked at the yearly data, again, we see a definite seasonal pattern, and it pretty much repeats per year. We have high points here in the summer where we have increased production. So I decided not only to just try a naive forecast, which means I just used the previous time period, but I tried a naive 12, which means the seasonality is by year, so I predicted 1 year back. So when I'm looking at my forecasting values, notice these don't all start in the same point. So this one I could predict starting in the 2nd month. This one I couldn't really start until I had an entire year's worth of data to go back one from. So I couldn't start until the January of the following year. And then a 3-period moving average, in this case, since I said it's 3 periods, means you take the three previous time periods and you just average them. So it's just that simple. And as we move down the list, it just keeps moving that average down. And so this one, again, I can't forecast for the first 3, but once I get here, then I'm okay. So when I start reporting things, if I wanted to actually report my training error measures, I'm going to start here in this year because that's where I can actually collect data for all of the different forecasts that we are comparing. Just to kind of show you how I came up with the different measures. First I found the forecast error, which is actually minus predicted or forecasted value. So we just subtract actual minus predicted. And I did it, everything's in 3s because I have my 3 different forecasted values here. We also need the absolute, so all this does is it removes the negatives. So here, like this 34 just becomes 34. And then we also have a measure of the ratio of the error to the actual value itself, and this just gives us a scaled value, and that's used for the MAPE, or the percentage error. So I did this by just taking the absolute value, which we already calculated, all the way back divided by the original value. So for all of these, that second number is still the same. It's all the way back to the the original value that we had. So once I have all these intermediate things, my forecast error, my absolute forecast error, and this ratio, I can pretty quickly come up with the actual values here. So my mean absolute, the mean absolute error is just taking the absolute error and dividing it by the total number. My mean forecast error is going to take the forecast itself, that error, and it's going to divide by the total, and it's not using the absolute. And what you'll see that's different here is that this takes into account the negatives, so these numbers are going to be typically a lot smaller because all this added everything, even if I had a negative error. And if these turn out to be negative, then that gives us some information. In that case, we know what's going on with the model. So notice we had our little cheat sheet over here. So we can see if it's positive, then we under forecasted, and if it's a negative number, we've over forecasted. Our number was actually too big. All right, the next one is our percentage, and this is going to use that percentage column that we found. So it's going to take our absolute value of E divided by the forecasted. Let me put it over here in the training one. So we can see I'm using this column here, and I'm going to divide it by the total again. So everything is always divided by our total sizes, so we can kind of get a ratio. And then we multiply by 100 just to get this in terms of not a decimal, but this is a percent. So this is a 4.7 percentage error. Notice if we start to look at these, we can see our naive is doing pretty well. So we have a pretty small forecast error on our MAPE, which again is one of our most popular ones that we look at. And in particular, the seasonal one, it does better than just the regular naive of 1 period ahead. But both of them actually are doing better than our fancy, quote, more sophisticated 3-period moving average. For our root mean squared, we're going to take our errors and we'll just do the sum of squares. So if we look at the formula for the root mean squared, I have to take all of the errors squared. And so I can do that with a sum of squares function. So I don't have to create another column over here that is the squares, but I could if I wanted to. So now I have all my measures for the training, and then I also did it for the validation data. And when I went through the data set, I just made all the validation yellow to help me keep track a little easier. And again, this is the validation is the one that you really want to have reported. Finally, our MASE, this is our one that we can use to help it be a little bit more or actually should I help it handle the zero counts if we happen to have any zero predicted forecast errors. We can't divide in our MAPE over here, we can't divide by the Y if it's zero. So what we do is we take a ratio of the let's go back so you can see over here, the MAE for this particular one that we're looking for. In this case, I wanted the 3-period moving average. And you look at it over the naive for the training. That's a little bit different, but we're going to use the training as our baseline, considering that's what we kind of fit the model on, and we found one that worked really well. And then we'll divide it out from the actual 3-period MAE. And I did this for the naive, and I also did it against the naive for M is 12, and we can see, it performed better against the naive, but for this one actually it didn't. That maze does a little bit better, and our maze values over here, we can see if it's less than 1, then it has a lower average error than the naive. So essentially it's doing a little bit better if it's less than 1, and if it's greater than 1, then it has poor performance relative to the naive, and both of ours are greater than 1. So that naive is doing better, which we can tell by all these other measures that we have. The last measure that I showed you was a tracking signal, and this is kind of used to kind of see how the forecast is doing as we move forward. So I went ahead and just copied 1 year of data. This is the final year, and the final forecast specifically for naive is equal to 12 because that one seemed to be working pretty well. And then I've copied a couple columns over here so that we have them. So here's our forecasted value, and here's our error, so we just take the difference, and then here's our absolute. From that, for our tracking signal, we had, let me get back to our formula over here. We're going to take the sum, what we call the running sum or the cumulative sum of the errors divided by like a cumulative MAD. Okay, so we're looking at the mean absolute deviation, and we're going to compare that to see if it's within 4. If it's greater than 4, we see under forecasting. If it's less than 4, then we see some over forecasting. What we're seeing here, we're going to look at this cumulative error, and we're going to look at the MAD. Both of these are calculated based on cumulating up to the row that we're on so far. So you can see I've made a formula so that it just adds up the forecast errors, and then for the absolute deviation, it just adds those up from here. So this is mean, so it's taking the average, and then this is just cumulative, so it's just taking the sum. So those formulas are slightly different. This one's mean, and this is just sum. But for each one, then, we just take this ratio in order to come up with our final conclusion, and here we can compare these tracking signals to plus or minus 4.